So for the thermal lab, first thing we need to talk about is heat. So let's say I have two systems. So one is a hot system, the other one is a cold system, meaning that this one is at a higher temperature than this one is at. So what happens then is when these two systems are in contact with each other, I have a transfer of energy from the hot system to the cold system via what's called heat. So heat is what we call Q on these variable y's. This is then the transfer of energy from a hot system to a cold system because these two things are out of thermal equilibrium with each other. Now, what will happen then is that this heat will continue to flow until eventually these two systems become into thermal equilibrium, which basically means that once this system reaches the final temperature of T, and this system also reaches the final temperature of T, heat then no longer flows from the one system to the other system. So again, heat is specifically the flow of energy from a hot system to a cold system, and this process undergoes until these two reach thermal equilibrium, meaning that the temperature of the final systems are exactly the same. Now, since this is an energy, this thing has units then of joules. Now, what will happen to the thermal system as heat is flowing? Well, that's going to depend. So, what happens then is if I'm adding heat to the system, and let's look at the temperature of the system itself. So basically what happens is initially, if I start adding heat to the system, again, depending on where I start, what will typically happen then is there's actually a linear relationship between the heat flow and the change in temperature. So actually I call this change in temperature. So in this case, what happens is as heat is flowing into the system, the temperature then is changing linearly with the heat. Until eventually what happens is I come to a portion where as I keep adding heat to the system, the temperature actually no longer changes. The temperature stays constant, but the heat is still flowing into the system. Eventually what will happen then is this will eventually cease, and then I'll go to a linear relationship again between the heat and the change in temperature, till eventually this is also going to stop, where again I'm going to plateau, and then eventually this will go back into a linear relationship. So these portions where it is no longer increasing temperature, this is what's known as a phase change. So here I'm undergoing a phase change, which basically means that I'm either going from a solid to a liquid, or from a liquid to a gas, or from a solid directly into a gas. These are different types of processes that can happen. During a phase change, this is what's called latent heat. So energy then is being dumped into the system, but there's no change in temperature. Now, if we are going to do both parts of the lab like we were supposed to do, you would have seen that as well. In that case, we would have actually been playing with liquid nitrogen. Would have been a lot more fun, but unfortunately we couldn't bring liquid nitrogen home, so we had to skip that part. But basically what's happening here is you are changing the molecular structure of the system itself, and that takes a lot of energy to do so. So for example, if I'm going from a solid to a liquid, I have to destroy that solid structure, what's called a lattice. So it takes a lot of energy being pumped into the system to break that lattice to then create something which doesn't have a lattice anymore, which would be the liquid. These sections here, this is what's called specific heat. So the sections where the temperature is increasing as the heat is increasing, this is what's known as specific heat. Okay. Or just purely away from a change or a phase transition. So here, when I have a phase transition or a phase change, again, I put heat into the system, but the temperature is not changing. When I'm then adding heat to the system and the temperature is increasing, in that case, then this is what's known as specific heat. Now here, what this says then is that the heat flowing into the system then is equal to the mass of the object times what's known as the specific heat times then the change in temperature. So this is then mass of the object. C here is what's known as the specific heat. And then finally delta T here is just the change in temperature. specific heat. Specific heat is a quantity that is dependent on the type of material that I have. So, for example, if I have ice, ice has a particular specific heat. If I have water, that has a different specific heat than ice does. If I have water vapor, that has a different specific heat than water does and what ice does. So this specific heat depends on the type of material, it depends on the phase of the material, but it doesn't depend on the quantity of the material, because that's what this mass portion is for here. So this is, roughly speaking, this is the amount of energy that it takes to increase the temperature by 1 degree per kilogram. Okay. So this is specific heat. So specific heat is roughly the amount of energy it takes to increase 1 kilogram 1 degree Celsius. That's what this thing is. Now, what we're doing in this lab is basically taking two quantities, putting them together. So I have a hot system and I have a cold system, and then these are going to reach thermal equilibrium. Now, while this happens, we're going to assume that we have what's called a thermally isolated system. So what does a thermally isolated system mean? So a thermally isolated system just means that we're going to assume that all the heat flow goes from the hot system and into the cold system, and nothing is lost to the environment. So in this case, we're going to have here water. This is going to be our H2O. Inside of this, we're going to put our metal. But the metal is going to be the hot system. So this is going to be at an initial temperature of T hot. The water then is going to be at the initial temperature of T cold, meaning that heat is going to flow from the metal into the water. Okay. Now, again, we're going to assume that this is what's called thermally isolated. Which basically means that all of this is going to be completely insulated to the exterior. So whatever is happening out here, so the exterior, is isolated from what's happening on the inside, and the inside is isolated from what's happening on the exterior. Which basically means that we're going to assume, again, that all the heat which comes out of the metal is going to go into increasing the heat, or at least the final temperature, of then the water here. So basically, this is what's called calorimetry. So calorimetry. So calorimetry says then is in our thermally isolated system, the sum over all possible heats must be equal to 0. So what does that mean? So going back to here, what this means then is what? If I look at the metal's final temperature is less than the initial temperature, which means that it has a negative heat. So in that case, it's giving off heat. The water is going to increase its temperature because it wants to establish thermal equilibrium with the metal. So that final temperature is going to be greater than the initial temperature, which means that that one has a positive heat. So in this case, we're going to say then that the heat from the water plus the heat of the metal must all be equal to 0. Again, this is going to be a positive quantity, this is going to be a negative quantity, so if I take a positive plus a negative, that's going to be equal to 0. Okay? So, in this case, we're simply going to have then the mass of the water times the specific heat of the water times the change in temperature of the water plus the mass of the metal times the specific heat of the metal times the change in temperature of the metal must all simply be equal to 0. Okay. Now, in this case, we know the mass of the metal. We know the change in temperature. That's just going to be the final equilibrium temperature, which basically means that the final temperature for the water and the final temperature of the metal are going to be the same because this system is going to establish thermal equilibrium. We know the mass of the water. We also know the specific heat of the water. From here, the only thing we're looking for then is what is the specific heat of the metal. So, calculationally wise, so let's calculate that specific heat. So finally what I get then is, throw chalk all over my place, the specific heat of the metal is then equal to minus the specific heat of the water times then the mass of the where am I? Good. Of the water times the change in temperature of the water divided by the mass of the metal times the change in temperature of the metal. Now, again, don't worry too much about this negative sign because, again, the change in temperature of the water is negative because, again, the final is less than the initial. So this negative is mostly just to make sure that this negative here makes the whole entire thing positive. So, in this case, this is what we're calculating. So all we're going to calculate for this lab then is what? The specific heat then of the metal. We're going to do that for 10 times. From there, you want to find the average and the standard deviation. You also want to find the discrepancy because once you know what the metal is, you look up what the specific heat is of that particular metal, either in a textbook or online or any place that you want to. And then from there, that'll be the accepted value. You'll have your experimental value. So then you can calculate your discrepancies, so both the absolute and relative discrepancies. So again, this is heat. So again, heat is the flow of energy from a hot system to a cold system. This will continue until these two things establish some sort of equilibrium with each other. Again, in most cases, there's a linear proportionality between the change in temperature and the heat flow. Again, that's during the times where those things are changing, i.e. it's then talked about in terms of specific heat. But again, there are times where that thing flattens out, so meaning that there is no change in temperature when there is still being heat added to the system. That's called a phase change. In this case, we're not going to have any phase changes, so you don't have to worry about that. In this case, it is specifically just this, so you don't have to worry about the latent heat. The only thing we're talking about in this lab is then the specific heat. So again, and here, your metal is going to be your hot temperature. So this will be your initial temperature. Your water then is going to be your cold. So from here, you'll have to know this number and this number. But again, the final equilibrium temperature will be the final temperature for both the water and of the metal. So from there, you're just establishing what is that specific heat of the metal.